Okay, so let's continue our discussion for quantum mechanics for a quantum particle, in this case electrons. So we previously discussed on free electrons. Now, for the case of free electrons, the energy is continuous. Okay, so we're going to put now boundary conditions of the particle, the electrons, in a way that it can only exist in a particular one-dimensional location. And we do this by creating a wall, right? A potential wall where the potential in that one-dimensional box, the potential is infinitely high, right? So when you put the electrons inside, so the barrier at the edges here, the wall, the potential is so high that the electrons cannot escape out of it. All right. So that means that if this is between 0 and L, so the description of the wave function at 0 and L is 0, right? So at x equals to 0, the wave function is 0, and at x equals to L, the wave function L is 0. So that when you square it to get the probability, at this point is 0 and at this point is 0. All right? Okay. As I mentioned, at the boundary here at the wall, the potential energy is so high that the electrons cannot escape. And then we assume that inside the box, the potential energy is 0, right? So the electrons can move freely without any potential barrier inside the box. Okay, great. Now the solution for this wave function is that the wave function is equal to A cos kx plus B sin kx, right? A and B is a constant that we have to find, and k is the wave vector. And what is the formula of the wave vector? The wave vector here, as we derived in the previous video, is the square root of 2me over h bar. All right? Okay, now let's analyze this. Right, so if at the boundary conditions say that at x equals to 0, right, psi 0 is A cos k times 0 plus B sin k times 0, and this is equal to 0, all right, as our boundary conditions. So A cosine of 0 is 1 plus B sin k 0, and this is also 0. So this is 0, so A is 0, right? Okay, so now how about L? So psi at x equals to L is A cos k L plus B sin k L, right? From the first substitution, we get that A equals to 0, so this term is 0, right? So we have now only this term. So the boundary conditions say that at x equals 0 and x equals to L, the wave function is 0. So at x equals to L, the wave function, this one is 0. So B sin k L. Okay, so we have this relation. So then we have to find at which sign value that this is 0. And this is 0 when k times L is equal to n times pi, n being an integer. Right? It can be 1, 2, 3, 4, and so on. Okay, because sin pi and 2 pi, 3 pi, 4 pi are 0. Okay, so here we create, or we find a new requirement, okay, in addition to this description of k of wave vector, that in order for the wave function to satisfy a particle in a box condition, the k has to satisfy this relation. Okay. Now finally, when we substitute this k, you will have that k here is equal to n pi over L, and here if we put these two together, 2me over h bar is equal to n pi L, right? So the description of the energy will give us h square n square over 8m L square. Okay, and if you solve this, you will get this term. Okay, let's elaborate here. So if 2me over h bar is n pi L, so h bar is if you want to find the energy of a particle in a box, so we have to square this, so 2me over h bar square, and this is also square, n square, just put that, pi square over L square, so the E would be n square pi square h bar square over 2m L square. Now we can further simplify this, that h bar is equal to h over 2 pi okay, and this pi and pi and this pi is cancelled out, so you will get n h bar over 8mL. This is the E at particle n. Okay, so this means that the energy at a specific n value is a function of the n square h square over 8mL. M is the mass of the particle. L is the size of the one-dimensional box. Okay, so if you compare the energy description with the free particle, now we have the n square a term here, which means that, which by definition that n has to be an integer, right? N has to be an integer, which means that the energy level inside the particle in the box is a function of n square, which is an integer. So if this is n equals to 1, then you cannot have n equal to 1.1, 1.2, 1.3, and so on. You can only have n equals to 2, n equals to 3, and so on. Right? Okay. And if we go back to the then the description of the wave function, and the wave function would be psi x. So we have b from here, because a is 0, so we have only b. Sine k now is described as n pi L, n pi over L times x, right? So this is our wave function. So if n equals to 1, it will give you this wave function. If n equals to 2, it will give you this wave function. It's being 0. This is pi. This is 2 pi. If n equals to 3, it will give you this wave function. Alright, this is 0. This is pi. this is 2 pi, and this is 3 pi here, and so on. Okay, so if this is the energy level now, right? The fact that at these edges the value has to be 0 create a condition that the energy has to be discrete, right? It cannot be it's no longer continuous. So once the particle is inside the box, the energy level is discrete, because n has to be an integer, right? And this is because you have the particle inside the box with an infinitely high potential barrier. So what do you take from this formula? Is that as the n increases, the energy increases. As the L decreases, the length of the box increases. Sorry. So as n increase, the energy increase. L increase, the energy decrease. All right.